So it's my turn to welcome you all to day 2 of this Excite workshop. Day 1 was dedicated to electron microscopy, and today we'll speak about X-ray imaging. So just like today, the aim is to teach this course at the beginner level so that all of you have all the necessary information, for example, for preparing a proposal for transnational access. Today, I would like to start with a 5-minute primer. And the idea is to give you all the basic concepts and the terminology that you will need for the rest of the morning. And then I'll quickly introduce how this morning will look like. So to do X-ray imaging, you essentially need 2 things. You need an X-ray source and you need a detector. An X-ray source can be switched on, and after that, there is a conical X-ray beam that will emerge. This X-ray beam is very similar to visible light. That means that you can place, so if you place an object between the source and the detector, that object will cast a shadow. And that shadow will be darker if the object is denser. Now, the nice feature of a conical beam is that by placing a sample very close to the source, you can actually choose the magnification, or you will have an image projection that is much larger. The next step would be to rotate your sample around its axis. And at the same time, you will be acquiring images. If we take a look just at the images that we are registering here, so this is a time series of 2-dimensional projections. Then your brain has the impression to look at a 3-dimensional transparent object. And if your brain can do this, then you can also design an algorithm that does this reconstruction for you. So here at the dashed line, we can reconstruct a cross-section of this object. And we can not only do that at 1 dashed line, we can do that at multiple locations, here at 9 locations. But if we do that at about 1,000 or 2,000 locations, then you obtain the 3-dimensional volume that you see on the right. A 3-dimensional volume that you can then start turning in whatever direction that you like. You can also start cutting it up virtually according to any plane that you like. And you can start using this to do metrology. You can measure the wall thicknesses of the different pores. You can measure pores, the wall thicknesses. You can measure pore sizes. You can measure all feature dimensions that are of interest to you. Now, I'm speaking for a lot of geologists, so they might have recognized the foraminifera here, and they know how big this is. For the people that are less familiar with this type of object, I provide you this image to give you a sense of scale. So what you see is a finger of a person. On that finger, the greenish stuff is like a gel, and in that gel, you see this tiny white dot. Tiny white dot is the object we're looking at here. That means that with X-ray microscopy, you can actually obtain 3-dimensional information at a sub-micron level or resolution, and that in a non-destructive fashion. And obviously, those are properties that are very interesting. Certainly, if I tell you that this is suitable for any type of material, whether it's organic materials or whether it's polymers or earth materials or whatever, and it requires hardly any sample preparation. So the applications of this technique, they're very numerous. It goes from the analysis of the microstructure of materials over the assessment of product quality, metrology, densitometry, but also all these examples were static examples where you just look at one object. But since the technique is non-destructive, there is no reason why you couldn't do in situ or in operando studies where you're going to observe and quantify physical processes, so things that evolve over time. So this gives you a quick introduction about X-ray imaging. So everything starts with an acquisition, and the rest of my talk will deal with acquisition only. Acquisition gives you like a series of 2-dimensional projections over time. Those ones needed to be reconstructed to obtain an object in 3 dimensions. That's the subject of the next lecture, which will be given by Jan Alterman. And this three-dimensional data set will then need to be post-processed and analyzed, which is a topic that will be discussed by Ben Callow. These three steps are needed for any X-ray workflow. From then on, we provided 4 more time slots with pitch talks about advances and advanced applications, one dealing with compositional information, one with multi-scale information, one with more temporal information, and a last talk that discusses the challenges that are still present in X-ray imaging. So without further ado, I will speak about or attack this very first section, which is about image acquisition. Acquisition is key because obtaining high quality raw data makes it much easier to do a good reconstruction and also much easier to do post-processing afterwards and get a valid interpretation of your results. So acquisition is a point where you need to pay some attention to. First thing to know is that X-rays are electromagnetic waves. So it's actually the same thing as visible light. The only difference is the wavelength. So visible light, we know we're about, let's say, between 400 and 700 nanometers. Here we're between 10 picometers and 10 nanometers. So it's a very small wavelength. And since the energy of a wave is inversely proportional to the wavelength, these small wavelengths imply that X-rays have actually a very high energy content. High energy content that allows them then to penetrate materials, which is a property that we needed to probe their inner microstructure. These X-rays can be generated in an X-ray source via exactly the same mechanisms than those that were discussed yesterday by Oliver and also by Erik Hellebrand. So an X-ray source is nothing more than 2 electrodes that are put inside a vacuum chamber, and you apply a very high voltage difference between them. This voltage difference will cause electrons to escape from the cathode, to be accelerated towards the anode, and to impact that anode. And there many processes take place. So there are secondary electrons generated, backscattered electrons, all things that were discussed yesterday, but also X-rays. And those X-rays will leave in the form of a conical beam on the other side of the target. This is one configuration which is called a transmission source. If you position the target, so the blue block, at an angle, then the X-rays don't have to go through the target, but they can leave from the side. But whatever, that's a reflection source. But whatever the configuration of the source, in both cases, you have a conical beam that is coming out of this X-ray source. The conical beam can directly be used, for example, in a laboratory setup in a cone beam configuration. So there the beam radiates sample, and behind we put a planar detector, so a 2-dimensional detector. That's the configuration that I also shown in the introduction. In an industrial or medical context, they basically position an additional collimator between the X-ray source and the sample. Therefore, you create actually a triangular plane. This is called a fan beam. And that plane allows you to precisely position your light sheet, let's say, where you want it, and also to control the doses on the patient. There is a third configuration which I give you for completeness. That's the parallel beam configuration. So here there is no conical beam. The beam is all the photons, they have a parallel trajectory. That's what you encounter in synchrotron installations. To give you an order of magnitude, the laboratory tomography, so the top row on this slide, gives you about 10 to the power 12 photons per second, while in a synchrotron, you have about 10 orders of magnitude of more photons. That also means that experiments will be much faster and that you can do applications that are impossible in a lab configuration. Anyway, the shape of the beam defines how you magnify your image. We already mentioned that if you have a cone beam geometry, then the relative position of your sample between the source and the detector defines the magnification of that sample. If you have a parallel beam like in a synchrotron, obviously that doesn't work. You don't have any geometrical magnification. So there you need to position a lens somewhere, an optical lens, which will magnify the image before it reaches the detector. And there is no reason why you cannot combine both. So you can combine geometric and optical magnification, and that is done in so-called X-ray microscopes. That allows you to have sub-micron resolution for actually a very short instrument length, because the source to detector distance can be smaller. If you want to reach more than sub-micron resolution, but you want to go to, let's say, 10 or 20 nanometer resolution, then you need to go to another technology. And you need to put, for example, zone plates or capillary optics in between your sample and your detector. Whatever the magnification strategy, the key on forming an image is nevertheless that the X-ray beam interacts with your object. And so how does an X-ray beam interact with matter? There are many things that are going on. The very first thing is, for example, photoelectric absorption, where an X-ray beam kicks out one of the electrons from its shell, and another electron takes its place, hereby emitting a characteristic X-ray. There's also Rayleigh scattering, where a beam bounces off, let's say, on an electron and just changes direction but doesn't lose energy. And there is Compton scattering, where the beam does kick out an electron, thereby it loses energy, and therefore the continuing beam has actually another wavelength and energy content. There are other mechanisms at play, but what they all have in common is that they lose energy. They cause a loss of photon energy. And that loss of photon energy, we also call it attenuation. So since an X-ray beam interacts with electrons, it's not a surprise that the amount of attenuation, so the amount of energy that you lose, that this one is depending on how many electrons you have, or in other words, on the Z number of your material, the atomic number. And the higher the atomic number, the more stopping power a material has, and the higher the attenuation of that material will be. I'll give you a schematic of that. So here at the left, a very low attenuating material, for example, hydrogen. If you take a hydrogen atom, it only has like one electron orbiting around the nucleus. So therefore, there is a very low interaction between the atom itself and the surrounding and the X-ray beam, and therefore the beam makes it through almost unharmed. So there will be some photons that are stopped, but it's only a minority. On the other hand, at the right side, you do have a highly attenuating material, let's say uranium. You have a very dense electron cloud, and so a high number of incident photons, they get stopped, and only a very small portion of the beam makes it through. So the proportion of the beam that makes it through, that is expressed by the only law that I will speak about today, is Beer-Lambert's law. So it says that the intensity of the beam that is leaving your sample is actually proportional to the incident beam. So if you do not have any incident beam, then obviously you do not have a signal at the end behind your sample. And that incident beam is attenuated, so it's an exponential function, where in the exponent you see mu times d. Mu is the attenuation, which is material dependent. So a higher density material will attenuate more, and d is the path length. So if you traverse a thicker sample, then obviously less light will make it through. So that is one of the most important laws, and that's also the law that is underlying everything related to reconstruction, which will be discussed afterwards. Now, this beam makes it through the sample, but then we still need to detect it. And to detect it, there are essentially two strategies. Strategy one is the indirect conversion, which you see illustrated in the movie here. So in indirect conversion, you have X-rays that are coming in, and they impinge into a scintillator. The scintillator will absorb all the energy of all the incident photons, and then it will re-emit that energy under the form of visible light photons. Those visible light photons then are detected with a classical camera. So it can be a CMOS camera, can be a CCD camera, doesn't matter, but it's used to form an image in a visible light spectrum. The opposed to this strategy, you have the direct conversion, which is illustrated here, where photons, they're actually directly converted into an image. Obviously, direct conversion has some advantages because there is one conversion less. You actually can have images that are more neat and of higher quality. However, the current technology, the only thing that is currently implemented in commercial equipment is the indirect conversion. That works, that's a very mature technology, it works perfectly. And so in any of the tools that are available within the Excite network, it's actually indirect conversion that is used. That's a technological standard. On the right side, so the direct conversion, that's a technology that is still under development. It's in many labs, including ours. We're looking at this type of technologies, and we hope that this will be the next big thing. So how does this look in reality? In reality, you have an equipment that's about, let's say, 2 meters in length or metric in length, where on the left here you see an X-ray source. X-ray source creates the X-ray beam is about, let's say, 60 to 80 kilograms in weight and something like 60 centimeters in length, something like that. That will emit a beam that's going in this picture from the left to the right. The first thing that it will travel through is a sample. The sample that is positioned on a sample holder, and that will rotate. A sample, in this case, it's a millimeter-sized sample. In reality, the dimensions of a sample, they depend on the instrument that you're using. For sub-micron resolution, I highly recommend millimeter-sized samples, but in other tomographs, you can put samples that are tens of centimeters in diameter. Bear in mind that the resolution of your scan is about, let's say, the diameter of your sample divided by 1,000. So on a millimeter-sized sample, you reach a micron. On a 10 centimeter sample, you'll be, what is it, 10 times bigger, so 10 microns. Then, if we move further to the right, then we come to an optical component. So here, this lens box that is only needed if you want to combine geometric magnification with optical magnification. In this case, that was the goal. So this is an X-ray microscope, and it's meant to obtain a sub-micron resolution. And at the right, so there is a CCD camera. So like I mentioned, this is an indirect conversion mechanism. The scintillator is glued onto the different lenses here, where the thickness of the scintillator is adapted to the magnification of the lens, and then the signal is magnified and impinges onto the CCD detector. So this is how it looks in reality. If we again look at the schematic, at the left you have the X-ray source, then you have a sample that rotates. You have the geometric magnification, which cannot be excluded in a lab tomograph. Then you might have an optical lens, but it's not mandatory. And then you have a detector on which you will collect images while you're rotating the image. So the next step would then be to take this image, this set of images, and go towards reconstruction. But that is the topic of the next lecture by my friend and colleague, Jan Alderman. So I'll stop here, and I would be very happy to take any questions if there would be any. Thank you.
Thank you very much, Peter. Are there any questions for this first part? Because it's important that you grab everything that was said to be able to follow the next talks.
I do not see the chat since I'm in full screen mode. So if you have questions, please speak up. If you don't have any, then I assume that everything was clear. And
there is a raised hand from Liana. Liana?
Yes, thank you. I just have a question. You mentioned that obviously because of hydrogen being have a different attenuation. If you would have samples frozen inside of ice, would you be able to use that as a transmitting background and still necessarily go through it without actually losing resolution? It means you could actually scan bigger pieces of ice or select parts of your ice which are just in the center versus you know, that means in a rock core you can't do that, but maybe in an ice core you could. Is that possible?
The main, well, there are two things. There is obviously there is hydrogen, but there is also oxygen in water, in ice, and there is a density. So as soon as you freeze things, then the density still is on the order of, let's say, 1 gram per cubic centimeter. Which is half of a rock, so it actually is. It's a better condition than rocks, but it's still since in a lab tomograph, you if you put, for example, a 10 centimeter core in there, then the closest you can bring your source is half of that distance, so 5 centimeters, which basically means since your source is further away, so centimeters away from the core of your sample, that you're basically losing flux. So you can reach a higher resolution than if it would be a rock core. That's true, because the density is like half, but you will still need quite some time to reach a high resolution image. So it's on the time point that you will especially lose. But it's, for example, putting ice in an X-ray beam is not a problem. You can put ice inside a small chamber at for example, liquid nitrogen or so, using for cooling, and it's not that the X-ray beam will immediately melt it. The energies are way too low for that. To give you an idea, like X-ray sources, let's say the most powerful sources that are out there are something like 300 watts of maximum beam energy. So with 300 watts, you don't vaporize water immediately.
Thank you.
You're welcome.
Any other question? Okay, then if something would pop up, you feel free to send us via mail or contact Peter directly. So thank you, Peter, for this interesting and very good introduction. And we will now move on to the presentation of Jan Aalterman from Ghent University, who will then continue with the part on reconstructing data.
Okay, can everyone see my slides?
Yes, we can.
Okay, so